Remember torques? Torques are rotational forces. We talked about them last semester. So a torque can also be exerted on a current-carrying conductor. So let's consider a rectangular loop here carrying a current in the presence of a magnetic field. So we have our magnetic field pointing in this direction, and we've got a rectangle here, and we've got our current moving around counterclockwise here. And so this side of my rectangle we'll call length A, this side of my rectangle we'll call length B. And so the forces on the side of length A, the magnetic forces experienced on these sides here, are 0 because the current is parallel to the magnetic field. So if you remember, the magnetic force on a current carrying wire is equal to the current times the length of that wire, B sine theta, where this angle theta is the angle between the current and the magnetic field. So if they're both in the same direction, theta is 0, sine of 0 is 0. So there would be no magnetic force acting on these components, but there is a magnetic force acting on the longer sides, side B. And those magnetic forces are operating in such a way that it's going to cause this loop of rectangle, this rectangle here, this loop of current to actually spin around in this direction here, okay? So let's think about the forces that are acting here. So if I've got, let me move over to this side. I've got my first right-hand rule. Let's see. And so if this is the direction of current, then my thumb is going to point in the direction of the charge carrier, which is the electron here. So my thumb is pointing down, my fingers are pointing in the direction of the magnetic field, and maybe actually it works better if I'm doing it this way. There we go. And so then the magnetic force from the negative charge, the charge carrier, is not going to be out of my palm toward you, but rather into the board, pointing away from the top of my hand. So the magnetic force acting on this side is actually going to be into the board. So we'll call this Fn on that side. The magnetic force into the board on this side. And so over here we've got the opposite direction. So we've got current this way, so my charge carrier has a speed upward, okay? B, my finger is pointing in that direction, and so then the top of my hand is giving me the magnetic force on my negative charge, and so that's going to be out of the board towards you, okay? And so then that's going to be F, out. And so we see that on this side then, because my current is going upward compared to the magnetic field, that there's going to be a force pushing this loop into the board. Over here, there's going to be a force that's pushing the loop out of the board towards you. So this whole thing is going to spin around, and we're going to get a torque acting on this loop. Okay, and so remember that the torque is equal to this quantity R, which is the distance between the pivot, which is going to be the center of our loop here, and where the force is applied. Okay, so this distance R is going to be this half distance here on this length A, okay? And then the F, that's the force that's being applied there. And then the angle here, that angle is the angle between your R and your F. So here, that angle is just going to be, well, in this particular case right here, that angle would just be 90 degrees. So, let's consider what the torque is going to be on this loop right here. So remember that the sum of our torques is what we're looking for. So let's calculate the maximum amount of torque that this loop is going to experience. And so we're going to have a torque acting on this side of my loop and a torque over here, so you have to sum those up together. Okay, so I'm going to call the force acting on this side here force 1. And so the torque on this side of my loop is going to be F1 times, and this is our magnetic force, times R is the distance between my pivot and where that force is applied, so that's going to be half of this length here, so A over 2. And then I have to add my torque coming from the other side, plus F2 times A over 2, okay? And so this is going to be, well, the forces acting on these sides here, those are magnetic force, and that's our current times the length of my wire times B sine theta. And in this case, in this equation for the magnetic force, okay, which is what these F's are right here, the equation for the magnetic force, that angle theta is the angle between my current and my magnetic field. And in this case, for our currents running on side B, the angle between the magnetic field and the current is always going to be 90 degrees. Okay, so sine theta is going to be 1 there. So my magnetic force that I can replace here for F1 and F2, that's just going to be I times the length of that side, which is B, times the magnetic field strength B times A over 2. And then I have the same thing for the other force. Okay, I, B, little b, big B times A over 2. And so we sum those up together. And so then we get that our maximum torque that we could have is going to be I times B, little b, big B, A. Okay, now, actually maybe I'll write it this other way. Maybe I'll write it I times big B times little b, little a. Okay, and little b and little a, those are the sides of those are the sides of my rectangle here. And so this just becomes the area of my loop. And so the maximum amount of torque we would experience would be equal to I B times A, where A is the area inside my loop. Okay, I is the current, B is that applied magnetic field. Now we can make this more general, and the general equation for the torque that is experienced by a current carrying loop is equal to N, where N is the number of coils, or the number of turns of this wire. So we could wrap up this wire many times on itself, and N would be the number of turns, or the number of times you're wrapping this loop around itself. So in this example, we've only got one loop around here, but we could keep on coiling up our loop and get to many more turns if we wanted this number to be greater than 1. Okay, and so the torque is equal to the number of times I've wrapped my loop around itself, times the current, times the magnetic field, times the area encased or enclosed by that loop, times sine theta. And this angle theta here is the angle between the perpendicular to the loop and the magnetic field. So in this case, the vector perpendicular to the loop would be pointing out of the board toward you. Okay, and so in this case, the vector perpendicular to the loop pointing out of the board towards you and the magnetic field vector are at 90 degrees with each other. And so sine theta would be sine of 90 degrees, and that would equal 1. So let's use that idea to calculate the torque on a circular loop in a magnetic field. So here we have a circular wire, only one loop of wire here, so we're not coiling it up a number of times. So we've got one loop of wire here, and it has a radius of 1 meter, and it's placed inside a magnetic field with a magnitude of 0.5 teslas. And the normal, or the perpendicular to the plane of this loop, makes an angle of 30 degrees with respect to our magnetic field. And I is going around here in my loop, the current, and that current is 2 amperes. And so we're asked to find the magnitude of the torque on this loop with the current running through it with the magnetic field that's not even perpendicular to the plane of this loop. So we can use our expression torque is equal to the current times the area of the loop times B times sine theta. So in the previous example, we ended up having a value n here, where n is the number of turns. We only have one turn here. Okay, so our current is just going to be our 2 amperes. And then A, that's the cross-sectional area, or the area encased inside my loop. And since we have a circle here, that's going to be pi times the radius of this loop squared. So pi times 1 meter squared. Okay? And then times our magnetic field, which is 0.5 teslas, times sine of 30 degrees, where this angle is the angle between our magnetic field and the perpendicular to that plane of the loop, okay? And so, simply just plugging all those quantities in, I'm going to find that the torque is 1.57 Newton times meter. So if you remember from last semester, our unit for torque is Newton times meter. And so you can do the same thing to find the torque acting on any wire. The area of that current carrying loop might be a different area. It might not be a circle. It could be a rectangle. It could be a triangle. And the current will be that current running through that wire. And it's possible that you could have that wire wrapped around itself a couple of times. And so then that would increase the amplitude of this torque that's applied on our current carrying loop.